So yeah, I'm Chuck Willis, and as Glenn mentioned, we're going to be talking here about data at rest encryption. It's going to actually kind of follow on from the keynote that we just had. So I'm excited to get into this topic. So just a quick note about me. I think you already did a bit of the introduction. I am in the DC area, so I'm part of the OWASP Northern Virginia chapter. When there has been a Maryland or a DC chapter, I usually participate in those as well. I also a while ago created the OWASP Broken Web Applications project. It's a virtual machine full of web applications with various types of vulnerabilities. You can use it for training or for testing tools, that sort of thing. If you have any, I haven't updated that in a while, but the current version still works. It's a virtual machine, so it actually it gets more and more vulnerabilities as time goes on, as the libraries and components that it uses get older and older. So definitely check that out. And just a random fact, my favorite movie, The Blues Brothers. I'm originally from the Chicago area, so I think you're kind of required to like that movie if you're from that area. So I'm going to let Weiss introduce himself.
Hey everyone, my name is Weiss. I spent 20 years in the InfoSec community and focused mostly on incident response and threat countermeasures, as well as encryption and cryptography. I'm based in San Diego, so part of the OWASP San Diego community. And I've lived in Germany, the US, Singapore, and Japan. And randomly, my favorite pizza topping is, boringly, cheese.
I'm glad you said it. I wasn't gonna call out the boringness of the cheese topping. So here's a quick note of what we're going to talk about. So just really a quick primer on cryptography and encryption and key management, just to kind of make sure everyone's on the same page. And then Weiss is really going to go into detail on kind of the issues with the current data at rest encryption approaches that are used, and why that's a problem. And then I'll come back at the end to talk more about some alternative approaches that can help in kind of closing the gap that's there. We'll also have up till the end of the hour as far as for Q&A. So if you've got questions, please submit those through the Whova platform. And also, keep an eye on that as far as if you see questions that you're interested in hearing us answer, upload those so that way they'll kind of work their way to the top, and Glenn will provide those at the end. So cryptographic failures, you may know that from the new 2021 OWASP Top 10. So you can see that it used to be kind of rolled into a bunch of other things as part of sensitive data exposure in 2017. But now it's been broken out into kind of its own separate line item on the OWASP Top 10 as cryptographic failures, and it's also moved up in popularity. It's gone above injection and really above everything else other than broken access control. So it's a very common problem nowadays that people are recognizing. I think it's been around for a while. It's just that it's become more to the forefront. Maybe partially because we're trying to deal with things like SQL injection and cross-site scripting a lot better as far as kind of at the framework layer. So as those are less common, then we see access control and cryptographic failures become kind of relatively more common. And if you look at the documentation for the OWASP Top 10 that's on the website, the first scenario here that's shown is exactly kind of what we want to talk about today. So in this case, the example is an application that has credit card numbers that it wants to protect, but the way it's protecting them is it's got automatic database encryption happening. So there's transparent encryption at either the database or the files kind of block storage level, and therefore, because it's automatically getting encrypted and decrypted, when you have a SQL injection flaw in the application, it's just going to pull out all the decrypted data. So even though it's encrypted, it's not providing protection against this type of an attack. So, like I said, cryptographic failures have been around a while. So you might think they're the new kid on the block, but in reality, they're more like the upper right corner here. It's the current version of the new kids on the block as far as from their 2021 tour promos. So it's been around for a long time. So let's go a little bit more in detail into the situation. So, when you talk about cryptography, I mean, cryptography, existed long before computers. So they had, this type of instrument in the upper right is a thing for a Caesar type cipher, simple substitution cipher. You have the Enigma machines and other sorts of kind of mechanical and various sorts of cryptographic systems that were around. And so when computer security came around, well, computers came around, an obvious application for them was cryptography, but also an obvious kind of mechanism that could be used as part of securing computers was cryptography. And for some number of years, computer security really did focus on cryptography. They were really concerned about this type of thing of, hey, we want to encrypt some data that's going to be sent over an untrusted medium like radio waves. Therefore, we need to have the ability to encrypt it and decrypt it. And there was quite a bit of work has been done over the years into algorithms and modes that are very resistant to various types of attacks. So on the left here, lower left, we've got a kind of a diagram of the AES algorithm and kind of the rounds that it uses for encryption on the left and decryption on the right going up. On the bottom here, we have the cipher-block chaining kind of mode of encryption that allows you to be more resistant to changes to data or mixing of packets and things like that. So there's been a lot of work into that, and it's paid off pretty well. So if you're looking at kind of directly attacking kind of modern cryptography, it's very strong. Not to say it's perfect. Maybe nation states have the ability to do certain things, but I think even in those cases, you've got additional mechanisms you can use if you're really that concerned about the cryptography itself. So one example is you could layer encryption. So you could have multiple algorithms that are, used at different layers. Example of that might be, you might have a layer 2 encryption device that does kind of point-to-point VPN type connections, and then have a layer 3 or a session layer HTTPS type encryption on top of that. And so that's one option. I know the government sometimes will use multiple types of commercial VPN devices kind of layered on top of one another in order to provide additional security. So even if there's a vulnerability in, a Acme product, then hopefully it's not going to affect, the other product as well. So by having kind of these completely separate things layered on top of one another, you're giving yourself a lot better protection against attacks. And then for some algorithms like hashing algorithms or in like RSA, asymmetric algorithms, you can basically have keys as long as you want. So if you're really concerned about brute force, then you can make that basically impractical. If you're hashing passwords, you can make the process to hash the password down to the hash value take as long as you want. So to make password stuffing type attacks take longer, and so there's quite a bit of flexibility there. They've even got crypto algorithms that have been designed to be resistant to quantum computing. So even if quantum computers become practical, then you could potentially not have to worry about that as far as in your system. Might be worth looking at if you're building kind of a trust anchor that's going to be used for quite some time. And then there's also hardware cryptographic devices. So there's devices that'll give you secure random numbers and devices that will kind of come with pre-baked in keys that can't be extracted. So the only way to encrypt or decrypt data is to pass it to this cryptographic device, and it'll give you back the corresponding ciphertext or plaintext. But it basically prevents you from losing the keys because they can never leave the device. And you can see Microsoft, I believe, is making use of the Trusted Platform module on Windows 11 to do some of this kind of stuff, to have kind of that trusted root of the overall system. And then, so the only real limitation when it comes to kind of layering these things or other things that I just mentioned is performance. So if you're concerned about, how much your latency is going to be affected or what your bandwidth is going to be, then that's, the only thing really that you need to worry about. But the good thing is that, computers keep getting faster and networks keep getting bigger. So I think, you can pretty much wait a little bit and make up for that. So the problem really, as the previous, keynote speaker talked about, is really keys. So you need to have secure cryptographic keys. If you look in the bottom left there, we've got the guy from the Matrix, the key maker. So you've got to make sure that you're creating keys that are secure, and you've got a secure source of randomness or whatever to generate those keys. But it's more than just making the keys. There's a whole life cycle that goes around keys. So not just the generation that's shown here, but also where you're storing them, how do you distribute them, rotating them, expiration, all this stuff that goes into it. So you don't just need a key maker, you really need the key master. So these are just a bunch of quotes from various people that have said what I think's already been said today as well. Is really key management is the hard part, and my favorite one is the one in the middle here. That cryptography turns hard security problems into hard key management problems. So that's not to say that cryptography is worthless. I mean, it's certainly helping you, and it's giving you a way of making the problem more manageable. But it does not remove it entirely. You've got to worry about how are you going to manage the keys that are associated with this encrypted data and protect them appropriately, because that's where the attackers are going to go after. And then just again as a primer, just so there's two types of use cases really for encryption. So you've got the ability to have protection of data in transit, so while it's traversing the network. This is a simpler problem, I suppose, than what we'll talk about in a second, because there's a short period of time between at least when the data is encrypted and decrypted or signed and verified. At least that's the intention. So you can have ephemeral keys maybe that you use some sort of secure key exchange to come up with, as long as you have some sort of trust anchor to make sure that you're creating the keys with the right people. You do need to worry about what if somebody's going to capture all your network traffic and then try to analyze it later. So you want it to be resistant against attacks in the long term. But as far as being able to decrypt the data, you don't necessarily have to store the keys. You can, as long as you have them for the period of time, the short period of time that you need to decrypt them. And then the opposite is data at rest. So while data is stored, you need to worry about not just encrypting the keys, but because there's a long time between when the data is encrypted and then when it's going to be decrypted or signed and then verified, really the decryption keys, the storage and protection of those is very important. So you've kind of shifted the problem from once the data is encrypted and signed and everything properly, using the right algorithms, all that, you don't necessarily need to worry as much about confidentiality or integrity of the encrypted data, but you do need to worry about that for the keys. Good thing is at least keys is a much smaller piece of data that you need to worry about than kind of arbitrarily long documents and other things. So the good news is that data in transit is really basically a solved problem. For the fact is that if you're communicating with some other system on the network, you generally are going to use TLS or maybe one of its predecessors, and there's a well-established mechanism for not only kind of establishing keys and using the right algorithms, but also for a certificate authority system and how you can do that. And web browsers have their built-in certificate authorities, but if you don't care, you don't necessarily trust all of those certificate authorities, then you can have your own kind of more minimal set of certificate authorities that you're going to trust and use as part of your system. So that's really the good news. And so now I'm going to kick it over to Weiss to really talk about the rest of the problem.
Thanks, Chuck. So on to the bad news. And I hate to be the bearer of bad news, but I think most of the community has known sort of this core problem for a while, and it's sort of now becoming more prominent as we have sort of more modern approaches. But the key takeaway here is most data at rest encryption solutions are ineffective against modern threats. And that's primarily because they're built on what's referred to as a central implicit trust model. The idea being that the server and the people who administer a server, whether it's a database server or a file server, have the ability to access data in the clear or in plain text in order to perform their core job functions. So as you can imagine, this is something that we definitely want to tackle. So moving on, I'll cover a little bit about the central implicit trust model. Again, the central implicit trust model essentially suggests that key system processes and users have access to plain text data in order to perform a number of job functions. It could be to administer a database server. It could be for the database server to operate so that it could perform its core functions. So this means that folks like database admins, system admins, database server itself, the hypervisor host if you're running in a virtualized environment, administrator, you're working with a very prominent and they're sort of helping you manage your infrastructure, or you have cloud administrators on site with cloud access, or the cloud provider. All these individuals have the ability to view data in the plain text. That's another reason which we'll unpack in the next few slides. The other thing I'll mention before we move on to sort of what's bad and some key examples of how others are exploiting this sort of flawed implicit trust model is that it happens to be the antithesis trust model. For trust model, the whole idea is that trust no one. There should be no implied trust system, process, or an individual. Except the central implicit trust model is built upon the exact opposite, which is we trust everyone and allow them to be able to access data, again, in the plain text. So you might be asking the obvious, well, what's the problem with the central implicit trust model? Well, consider two scenarios. I'm going to walk you through first is sort of logical vulnerabilities. And then I'll walk you through a number of application-specific vulnerabilities. So starting with the logical vulnerabilities first, if you have a security incident involving, say, as Glenn mentioned earlier, an insider threat. Say you have an employee with admin access. The intention may not be nefarious, but they have admin access to a database or a data warehouse, and they accidentally, export the data into a file share, or maybe it's a nefarious intended individual. They have access to the plain text by the sheer virtue of the job that they're performing as a database admin, or a data warehouse admin, or a cloud admin. Consider the next scenario of a supply chain attack. Let's say a provider that you're working with, whether it's a SaaS provider or a cloud provider, where you're literally just hosting your data. Imagine that they suffer a breach and they're compromised for a period of time. And that compromised environment is now exposing your data. And the attackers who've compromised the cloud provider then retrieve cloud administrative credentials. They have the ability to view the data in plain text. And then lastly, advanced attackers or data theft. Generally, you're talking about sort of nation state attackers or fairly more sophisticated attackers that have the time and resources to be able to compromise a network and ultimately systems. One of the first things that they do is they seek out credentials through credential harvesting. And once they have those credentials for the databases or the data warehouses or wherever the data of value may be stored, they then use those authorized credentials to be able to access data. They usually encrypt the data with a key that you can't access, and then they exfiltrate it, and we sort of know how that story ends. But the key theme here is that all these sort of attacks are enabled by the fact that the underlying systems that we rely on heavily to ensure that data is encrypted don't actually work and are not effective against these types of more modern attacks. Now I'll spend a few minutes covering application vulnerabilities, and I'll tie them to the various OAuth's top 10 list items. The first one is access control, right? An attacker can modify an access control check or metadata to get access to privileged accounts. And that's actually the number one thing on the list. And I'll actually give you a real world example of where this occurred in a couple minutes, but that's a very, very prominent one. The second area is around authentication. An attacker can perform a credential stuffing attack. Chuck mentioned that a few minutes ago as well, to gain access to privileged accounts and data. Very similar to some of the logical vulnerabilities that I mentioned on a previous slide. They're using some sort of vulnerability, whether it's literally theft of credentials or exploiting a vulnerability in the application software itself or in the structure. And that obviously ties to the list item number 7 of the OAuth top 10 list, identification and authentication failures. And then lastly, the other one that I want to highlight is injection. And SQL injection is, I think, like for the last 15 or 20 years, like the problem that, as obvious as it is to solve, and as much as we as a community have been telling people, like they just keep happening. But this is the use of a blind trust application framework as an example that an attacker can exploit to take a vulnerable query, right? Someone that all the right intentions when they develop the query, but unknowingly there's a vulnerability to be able to form a SQL injection attack. And as Chuck mentioned a few minutes ago, to extract data from a database, even though that database has encryption in it. And that's obviously item number 3 on the list. So moving on from the vulnerability side, I wanted to give you 2 real world examples. And as you can imagine, we could probably come up with hundreds of examples of where, either vulnerable applications been or this logical vulnerability. The first is I'll be talking about is Marriott. And this is the breach that they in 2018. If you recall, there was also another breach in 2020, but also 2018 breach first. They acquired another hotel, which apparently had been compromised back in 2016. So it took them almost 2 full years to identify that compromise. Start off as a spear phishing attack, and enabled them compromised a number of internal systems. They performed a bunch of credential harvesting, identified access, admin level access to data that's stored sensitive information about folks. Yes.
Sorry to interrupt. We have a tiny bit of lagging. Could you maybe disable the video so we hopefully have a better audio quality?
Sure.
All right, thanks.
Yeah, sure. Apologies for that. San Diego internet usually is really good, but today doesn't seem like it wants to cooperate. Anyhow, moving back, I'll quickly run you through the Marriott use case again. So Marriott, again, 2018, compromised via a spear phishing attack, which then led to a lateral movement within the environment, ultimately credential harvesting. And then they got access to database admin credentials, which allowed them to exfiltrate, they're saying up to 500 million guest records, which includes credit cards, personal name, information, addresses, and even some cases, even passport information and images of passport data, which, as you can imagine, I wouldn't want in anyone else's hands. And then again, in 2020, they had a much smaller scale breach, about 5 million records stolen, but the same sort of process. So, when you think about a company the sheer size of Marriott, with the amount of capital they have to invest in security, these types of attacks can happen even for organizations that are that well funded. And then the application vulnerability side, I wanted to highlight a SQL injection attack that occurred several years ago, impacting 7-Eleven, where attackers performed a SQL injection attack against a publicly facing web server. Ultimately, that enabled them to get access to a sensitive database that housed over 130 million credit card numbers, which are stolen. The good news in this situation is that the attacker was ultimately identified and then ended up, I think they're still in jail, I think a 20-year sentence. But that occurred back in 2010. And then more recently, not mentioned on this slide, but in 2019, 7-Eleven in Japan actually took to market a pay app. And they had a pretty critical flaw in the design of the application where password resets didn't require any sort of authentication. So you could literally open up the application, put in an email address, and ask for your password to be reset, and be able to right there in the menu window, be able to reset the password, which was a massive flaw for obvious reasons. Over $600,000 of consumer cash was stolen in that event, and they ended up shutting down the application and never reintroducing it to the market. So pretty catastrophic impact both to the business model that they want to approach and also all the poor consumers that are affected. So sort of in summary, when you think about the traditional encryption controls, we've been sort of asked to use over the last 10 or 15 years, like full disk encryption, transparent disk encryption, database encryption, cloud storage encryption, popular things like S3 encryption or blob encryption, which nowadays have been simplified to literally checking a box off in an admin panel, or file share encryption. They're not going to help you in these situations because they're designed for very different types of threats, and frankly, threats that are dated. So in most cases, we're sort of on our own. But that being said, they can protect you if someone wants to steal your laptop, or if you're running an old Commodore and they want to walk into your house and steal that. They can definitely protect against that. Or literally walking into a data center, whether it's one that you operate or that a cloud provider operates for you, and stealing servers out of racks, which is a highly unlikely scenario. The other thing is, and this was mentioned earlier, I think Anastasia covered it, maybe Glenn, you may have touched on it. A lot of these encryption controls do help you provide literally the checkbox. So I think as an industry, from an AppSec point of view, there's definitely approaches we can take to sort of mitigate the risk and have more robust solutions in place. But one of the areas that I'd like to see sort of more improvement is on the compliance side, whether things like GDPR or HIPAA or PCI, that those sort of bodies and frameworks start to take encryption and drill down into controls that are more effective versus what I refer to as checkbox solutions, like the ones that I mentioned on the slide here. So now I want to hand it over back to Chuck so he can talk about the better approach. Over to you, Chuck.
Sorry about that. Yeah, thank you, Weiss. Yeah, and I definitely agree with what you said, which is that, I would love to see the audit and compliance folks get more granular in kind of when they look at encryption, because it really is currently it's basically, do you encrypt your data or not? That's really seems to be the level of questioning that they have. But the reality, as I mentioned earlier, is, once you've encrypted the data, then all you've done is shift the problem. So now it's, okay, the data is encrypted, but how are you protecting the keys? And so that's really what we would like to see, kind of as an industry to move towards. Or sometimes you also get people that maybe don't understand the difference between at rest and in transit encryption. So they would say, oh, our data is encrypted because we use TLS, and well, that protects against some types of attacks, but certainly not all of them, as we talked about earlier. So really what we should be doing is encrypting data higher in the stack. So I'm hoping you guys can see my pointer, but if not, I'll just kind of talk through this thing on the right, where it's like, this is kind of the you think of it kind of like an application stack. So you've got bulk storage at the bottom. That's where the database stores its files. And then you've got a web server up here that talks to the database server. And then you've got, some sort of a client application, whether it's a mobile app or it could be a JavaScript, type client on a web page. And then there's a user that's, using all this stuff. So if what you want to be doing, if possible, is you want to have, encryption happening as high in the stack as possible, because what that's going to give you is that, fewer devices and that are going to see the data. So, I mean, you think in the extreme case, if the human, says, okay, well, I'm going to use some sort of code word instead of my, social security number that I'm going to put in, I'm going to put in a fake number, then obviously the encryption is happening all the way in his head or her head, and therefore none of these systems are going to see the real data. But, that's not practical unless you're, one of the Navajo code talkers, maybe from World War II. Most of the time you're going to say, okay, we need, an automated system to do the encryption, but we want to be happening, here at the JavaScript or client or the mobile app. And the reality, is that the more transparent the encryption is and the decryption is, then really the more exposure you have. So, down here at the bottom, if, stuff is encrypted at the, bulk storage type layer, then, it's only going to be kind of controlled by the keys that are used to, as far as who can access that, so that, anything that's on the database server is going to be able to access that bulk encryption because it needs to be able to access its files. But then there'd be other administrators and stuff that can directly access the bulk storage for things like backups. You have to wonder if you're encrypting at that layer, and so the files themselves are not encrypted, then probably your backups are not encrypted, or at least not encrypted in the same way. You might have to be separately encrypting your backups. So there's kind of more headaches there. So the next layer up is at the database server layer, where it's like, okay, that's where you would have, what's called sometimes transparent data encryption, but for some databases or any other sort of kind of database server type encryption. And that's a little bit better because there's, fewer people that have access to the database server than have access to both the database server and the bulk storage system and backups and stuff. But there's still quite a few people that have access to this. And in particular, the web application server has access to all of the data on the database server. And there's no way that, whatever's controlling this stuff is going to be able to know, who is the, ultimately the user that's trying to access this data and, what data they should have access to. So if you're, our goal is to try to segregate this data more at the database server layer so that, there's, so that things that, are connecting to the database directly are not going to have the keys they need to be able to decrypt all of the data. So this is kind of a picture of that. So what you end up with here is that you'll have some sort of a key server, so this could be something you build yourself, or, some of the cloud service providers have those sorts of things. Other commercial vendors have them as well. That is going to, interface with the user. So whether directly or indirectly, maybe through the client or something, there will be, some authorization and authentication that happens, so that they'll be able to, the key server will know, okay, this is the user that's trying to access the data, and therefore these are the keys that I'm going to give, that are appropriate for that user that can be used. And so ideally that would be happening here on the client, but it could potentially happen at the web application server, or in some limited cases, it could even happen at the database server if you've got kind of client-side encryption, client-aware encryption, I guess that's happening there, where it passes the keys through that some databases use. Yeah, so the idea is that, we're separating the data through the control of encryption keys. And so you could almost think of it kind of like a two-system control where, the application server itself is got, some access controls that's going to say, okay, this user is supposed to be able to access, this type of data on the system. But then, that's not sufficient. They also need to have the right keys that go with it. So now, what you do end up doing potentially is, implementing, authentication and authorization logic on both sides. But that's kind of the point here, is that we want to be more granular and get more specific. So the idea is that even if there's a SQL injection, for example, in the application that's going to basically bypass this level of authentication check, all you're going to get access to is a bunch of encrypted data, and the only keys you're going to have to decrypt any of that data is going to be the keys that are associated with that user already. So it's the data that they can already access. So, as I mentioned, this, protects you against, not just SQL injection, but also maybe authentication or authorization bypass types of attacks, what we used to call insecure direct object references, various types of application layer attacks and logical attacks as well, as Weiss talked about earlier. And then it also gives you some defense in depth. So you've got again, fewer people that have access to the keys, and hopefully, basically nobody has access to all of the keys. So your database server admins, your web application server admins, all the people that work at your cloud provider or other customers of that cloud provider, none of them are going to be able to, even if things are misconfigured or that cloud service provider is breached, or tokens or whatever that are used to essentially access some of these systems, get checked into GitHub or something, you're still not going to have the keys that you need in order to be able to decrypt the data or to encrypt data that's going to be used basically for the to add data into the database or update data. So just a simple example here is, let's say we've got a medical record system, and so the idea here is that we want to encrypt, some pretty sensitive data that's there. So we're not encrypting everything. We're probably not going to be encrypting like patient names and addresses and some of that other stuff. As Anastasia mentioned earlier, one of the limitations you'll have is that, if you're encrypting data, then it becomes more difficult to sort and filter and select down those. Not to say that it can't be done. There are ways it can be done, but there's definitely performance impacts. So we're going to say, really what we care about is things like, test results or diagnoses or other, sort of data values like that are pretty sensitive for this person and need to be protected by, HIPAA or maybe other sort of regulatory requirements. And so what we're going to do is we're going to have the system's going to create an asymmetric key pair for each patient. So, myself as a patient, I would have, a key pair that's created within the system that is going to, have that relationship that like we normally see in what we call public and private keys. In this case, we're going to call them something a little different because it's, I think it makes it more clear that we're going to have basically a read key and a write key. So we're going to have one key that is used to read data out of this system, any of these protected fields or attachments, and then a separate one that's used to write the data. And so the idea here is that, a patient application, for example, would only get the read key. So that way the patient can only read their data. They can't create any new lab results or sensitive data in the system, can't write themselves prescriptions, for example. They're only going to be able to read, their data, but they get to read pretty much all of their data because it's, it's their health. And conversely, a lab, for example, might basically be the opposite, where they can only write data. So they're not going to be able to read any of the existing data in that patient's file, or decrypt it specifically, I guess. But what they can do is they can write data. So they can create new documents or attachments that are kind of like lab reports or, values and things that associated with lab work. And the idea is that, they're putting that data in there in basically kind of like a write-only fashion. So they can't even read their own data after they've put it in there, although certainly they would, probably have copies of it on their own systems as well. And then a doctor is going to have, both keys. So they're going to need to both read the data that the lab put in, but also write, other data and diagnoses and stuff that, the patient is going to see. So they would get both. So the idea here is that, depending on how this is all implemented, you can have, you're going to have the, very granular access control around, these keys specifically for this patient. But then there's even just more general things that you can enforce that it's like, hey, the patient application itself, regardless of which patient is logged in, is only ever going to get read keys. So if you're kind of able to do some kind of additional layers of access control by saying that the patient application is never going to get a write key regardless of what happens, and vice versa for the lab, so that you're going to be able to ensure that you've got, like I said, those multiple layers to ensure that you've got as much trust as possible, that only the right people are able to do the right operations into your data. And so if you want to read more about a similar example, there's one in the MongoDB documentation where they talk about what they call field level encryption that we'll talk about a little bit, but kind of walk through exactly like, yeah, this is how we would set it up, and this is how you can implement it in order to ensure that you get the security controls that you want to have in place. So now we've got the general idea of what we want to do, then let's talk about how we could do it. So there's basically three options that you've got available to you, and to implement this type of encryption into a system. So the first is what's called column level encryption. So the idea here is that we're going to encrypt only specific sensitive columns, maybe credit card numbers, socials, passport numbers, whatever, and that way each of those columns will actually be encrypted separately. So you might have some people that can access credit card numbers but can't access passport numbers, and vice versa. So it gives you, again, a level of access control, not just for users as far as like database admins and stuff, but also potentially different systems. So your payment system, would have keys to be able to access the credit card numbers, but not access some of those other sensitive fields, perhaps. And so that's the idea here. So it's kind of more at the client level, or it could be at the specific user level as well. And again, we're getting that separation even against the database encryption, database administrators. And the key here is that the decryption and encryption is not happening on the database server, at least in the best implementation of this. So what you want is stuff that's really what generally these are implemented in the kind of client library that's used to access the database server. So in something like MySQL or PostgreSQL, there'll be a library that you use on the web application server kind of side to access the database, and the encryption is built into that. So you would, at this level, at the application server, provide the keys to that would then get passed through to the database server. So there's a few different implementations of this. This is a pretty common technique. So I mean, it's pretty much all databases support it. SQL, Microsoft has a couple different kind of variants of it, where they call it either always encrypted data or column encryption. On Google Cloud specifically has kind of implementations for both MySQL and PostgreSQL. And the reason they have that is because it's basically interfacing with their key management system. So it gives them the ability to kind of have that, a more centralized place where you're storing the keys. But again, in both cases, you can see, like, based on this URL, this is all client side. And by client side here, that could be up here on the actual client, a mobile client or a JavaScript client, or it could be on kind of the database client library that's accessing the database server. And then you can also do database client encryption on AWS. So here's an example of that. There's probably lots of other potential implementations. One thing to be aware of, though, is that I believe Oracle uses the term column level encryption for some of their stuff, but in reality, it's more like transparent data encryption, where it's happening kind of all on the database server, and it's doesn't have the kind of security properties we want here, where you can get more granular kind of control of the keys. So you do have to be a little bit careful with some of this stuff that different systems or database implementations are going to call things a little bit different, or use the same term for something a little bit different. So it's definitely worth doing a little bit of research on that when you need to. And so the next option is what's called field level encryption. And so this is basically sometimes people will say field level encryption when they really mean column level encryption, because what field level encryption at the strictest sense is it's basically more specific than column level encryption. You're going to have the ability to encrypt a specific data fields that are in a column, but you're not necessarily encrypting all of the rows of that. So we're going to have a specific fields that the data in that field, or maybe even data in other fields, are going to drive the encryption that's used. So for whatever reason, maybe we want to encrypt just the American Express credit card numbers. And so we could do that with field level encryption. Maybe we want to, encrypt only the credit card numbers that are associated with customers that are in Europe for GDPR type reasons. You could even do something with field level encryption where you could use different encryption algorithms based on, where the user is. So you could think of a world maybe that, in America, they mandate that you must use AES to encrypt data, but then in some other country, they mandate that you must use some other algorithm to encrypt the data. And so you would need to have more granularity there in what you're doing. So that's gives you the ability to meet those kind of use cases. And so again, it's not happening on the database server. Generally for field level encryption, it's going to be all the way up here on the client, although it could be down here on the web application server. But the key is that it's, again, not on the database server itself. And so there's really two main implementations of this that I've identified. So one is, MongoDB was really the pioneer for this. They created a whole kind of mechanism around this that you can read about in their documentation at this link here. And so they go into, kind of how you can set up this on the client side, and they have, full support for it as part of their client libraries that are used to connect to a Mongo database. And then Amazon does this as well, although strangely it's part of their CloudFront because they're basically doing field level encryption that kind of starts, I think, all the way at like the HTTP field level. And again, kind of with that idea that you're encrypting data as soon as possible in the overall kind of stack. So that's an interesting implementation that you can get into looking at their documentation. So those two, field level encryption and column level encryptions, are the two kind of automated mechanisms, I guess you could say, implementations that exist to do this. And so the last option is really, you just gotta do it yourself. So, we can do application level encryption. So the idea here is that, you've got logic built into the client, whether it's JavaScript or a mobile app or whatever, and it's going to do all of the, encryption and decryption. So this is, obviously the most flexible because you're, if building it yourself, you can do whatever you want. It's also kind of technology agnostic. You're not tying yourself to a particular database backend or cloud technology like we were just talking about with field level encryption. If you've got multi-platform type systems where maybe you've got multiple types of applications that are built on different platforms that need to access the same databases, then doing it as kind of at the application layer is helpful because it allows you to be agnostic to kind of what's underneath and what's above as well. So it gives you a lot of flexibility with the the cost of just being a little bit more work and complexity for you to deal with. So again, you're not encrypting the data on the database server. You're doing it in your own custom application logic. And what you can do is, like I said, this is kind of technology agnostic, but there are different vendors that can help you in implementation. So again, you're kind of tying yourself to that vendor, but you can find vendors that will basically be cloud agnostic. So you could use the same data encryption scheme, whether you're putting data on premise or in the cloud at Amazon or in the cloud in Azure, and allow you to move data around without being kind of tied to that underlying technology. So if you want to learn more about ALE, you could grab yourself a glass of ale and read up on a couple of these documents. So we've got a pretty good article here from InfoQ that talks about software architects and how you can use application layer encryption, and then a recent Forbes article as well that talks really about the specifics of what they call it entity level encryption. But the idea is that you're treating it as granular as possible in the data that you're encrypting and decrypting, and that allows you to be a defense against ransomware as well. So generally, ransomware, if it kind of gets into your system, is going to be operating down here at either like the bulk storage layer, or maybe some ransomware is kind of database aware, where if it was able to get database credentials, you could go and start encrypting a bunch of data in your database. But if you're if your data is, encrypted at a higher layer, then that's not going to necessarily help them. So now, I guess to be clear, so I mean, ransomware that just goes in and tries to ransom your data, they could encrypt the data down at the lower layer, and you're still going to have to deal with that as far as getting, through that hurdle. Hopefully, you've got good backups that are, kind of protecting against that sort of attack. So the really more concerning is kind of what we've seen this year, where ransomware has moved from just kind of preventing you from accessing your data until you pay, to also being able to like steal your data and potentially posting it online and doing other things with it. So the data theft portion of ransomware is what's this entity level encryption that they call it would really help you with. So just a few kind of parting words of crypto advice. So if you are involved in a cryptographic project where you've got to encrypt some data and take care of it properly, then here's our list of do's and don'ts. I'm not going to read through them all. Hopefully they look familiar, and there's lots of good documentation on the OWASP site and other places as well that kind of goes into the details. But really what it comes down to is that there are a lot of details you've got to get right. I mentioned earlier that the algorithms that we have today, things like AES and the GCM encryption mode are very strong, but there is opportunity for potentially some implementation flaws that could cause you to have issues. And this is my last slide. So I know we're basically at time as far as we're getting into the Q&A portion. So I definitely appreciate you guys all coming, and I hope that you've put some questions. If you haven't already, put some into the Whova chat, and we'll be happy to answer them as many as we can during this period of time. You can also feel free to reach out to us via email. Weiss and I are happy to help as far as responding to any questions that you have after the talk as well.